Okay, so multiplying this matrix by this, first row times first column, negative 0.6 times x1, negative 0.8 times x2. Second row times the column, very simple, it's 0.8 x1 minus 0.6 x2. You multiply a row by a column, first number in the row times the first number in the column, second number in the row times second number in the column. You keep that going till the end of the column. And the column had better have the same length as the row does, otherwise you can't multiply them. That's it. That's how you multiply a row by a column. Multiply a matrix by a matrix, you multiply every possible row by every possible column. Every possible row in the first one by every possible column in the second one. And the result always goes in that row and column of the second one. So first row, you've only got one column here, right? So first row times first column goes in the first row and the first column, right? That's here. Second row, first column goes in the second row and in the only column you have, the first column, right? In a minute we'll multiply a matrix by a matrix, so we'll have a second column as well. Okay? So if I had a second column here, well, I'd just do the same thing and I'd put the numbers over here in the second column. Just the simplest thing you can expect if you have this array of numbers, okay? Okay, so that's this. This is your, okay, now this is a transformation. So we kind of do this. We call this a transformation from one vector space to another, okay? Right over here. Okay? Your transformation is defined by this. V equals R2, W equals R2. You know what R2 is? Okay, here's R2. I mean, here's your depiction of R2. Here's a real axis. And here's a real axis, right? It's just like your XY coordinate system, but you can call it T, U, or whatever, okay? Call it anything you want to, okay? Points of the form x, y, with x is in R and y is in R, and R with, you know, the fancy R with the double thing over here, double stem or whatever it is the set of real numbers. I assume you know the set of real numbers. Okay? Yeah, integers, rational numbers, irrational numbers. I'll also mention R3 would be the form x, y, z. That'd be three-dimensional space, right? That's all we're talking about right now, but obviously I could define R17. I could define R84, but I'd run out of letters, so I probably better use subscripts for my, you know, my form here. But yeah, we'll worry about that later. Right now we're in R2. V is R2, W is R2, right? So we can say, okay, well, here I've got a space R2. And I'm mapping vectors in this space to another R2, which I'll call W. I've got a couple of R2s. I got to call them something different, so I'm going to call them V and W. Okay? And the rule is if I have the vector x1i plus x2j, which I designate by x1, x2, that this maps to a vector over here. Okay, now let's see what this thing does. Okay, I think, no, might not map it to here, but maybe. Okay, that this vector over here is this, and if A is this matrix, that's okay. Now, it's not obvious what properties this transformation has, but one essential characteristic is if I have a set of vectors, and we'll draw all the vectors, you know, we're going to represent a point by a vector from the origin to that point, okay? So all these vectors will start at the origin, and all these vectors will end up starting at the origin because, of course, if you have the 0, 0 vector and multiply the matrix by 0, 0, you're going to get 0, 0. X1, 0, X2, 0, you're going to get all zeros, no matter what matrix you use. If I had a bunch of vectors that all went out to some straight line from the origin, all the vectors I get over here would go out to a straight line. Okay? So in that manner, straight lines get mapped onto straight lines. So we call this a linear transformation. Now there are other reasons we call it linear, but that's a geometric reason that you can grasp onto, okay? Now, well, you know, to understand this completely, I'm just saying it right now, so I'm just, you know, starting your brain to work on it, okay? And maybe you see a lot more. And some of you are going to see more of it than others, but everybody needs to work through the problems and work on the problems, work through them in order to lock in what you think you might understand now, okay? You might recognize some of the words I've said next time, but if you haven't worked on the problems, you're not going to know them. So every day you got to build on what you got the day before, okay? You really got to do every assignment. I understand life can sometimes make that hard to do, and nobody's perfect at it. But that's how you succeed in the course. Okay, so that's the idea of a linear transformation, okay? There are all kinds of properties we can prove, but actually linear transformations we don't get to until late October. Again, what I'm giving you here, I'm showing you with the forest so we can work through the trees without losing track of where we are and how everything is connected to what we've done before.